Yes, class. Am I audible to all of you? Austin, Faiza, Pia, Humam, Madiha, Tarif, Rabia, Shahid, Shavez.
Yes, ma'am.
All right. So in the last class, we had started with LCR circuits. So in LCR circuits, we had seen that inductor, capacitor, and resistor were connected in series. That's why we call this as series LCR circuit. L is for inductor, C is for capacitor, R is for resistor. So one common impedance formula, common formulas for the generalized circuits we had seen. See, what will be the resistance? This is the net value of resistance. Now, XL minus XC or XC minus XL, this depends upon the value which is greater than the other. If XL is greater than XC, then you will write XL minus XC and vice versa. All right. So this is how we use the term resistance. Once we know the term resistance, we'll use the other formulas. Like current is equal to EMF divided by the Z. Instead of using the individual resistance, we will use here the Z. Tan theta and tan phi and cos phi also we had seen phase differences. Let's practice some questions. Questions we didn't practice, no? Okay, note down this question. Determine the impedance of circuit, or let's discuss this itself here. Determine the impedance of a series LCR circuit if the reactance of C and L are 250 and 220 ohms respectively, with R as 40. So you have all the data with you. The resistance is given as 40 ohms. XC is given as 250 ohms and XL is given as 220 ohms. See, XC is greater than XL here, right? So in the formula of Z, when we put everything R square plus XC minus XL whole square, we'll use XC minus XL. This one is greater. So this becomes 40 square. 250 minus 220. This becomes 30 ohm. So plus 30 square. This is equal to 50. 50. Note it down. One more question we'll see. See, written, now look at this question. This says that what will be the readings in the volt. So look, just pay attention to the values that are given to you. Look, the voltage here is given as 90 volt. So you have EMF's value as 90 volt, right? Resistance is given as 45. Now, whenever we find out the net current, whenever we find out the net voltage or any other thing, for the value of net resistance, I told you will have to use that formula, the formula which we discussed, the formula of impedance, right? That you have to find out. So for that, I told you there are two cases possible. Either XL will be greater than XC or XC will be greater than XL. Now look at this. In this question, value of XC and XL. XC is given as 4 ohm, XL is also given as 4. Now how will we solve this? Because ultimately XL minus XC, either of these two equations we had to choose one, right? Now see, this is what? This is a special condition which we call as resonance condition of LCR series circuit. That is, the value of inductance reactance becomes equal to the value of capacitative reactance. All right. So if you have this formula, when you will use it, XL will be equal to XC, right? So Z will be R square plus XL minus, let me replace XC as XL itself. Right? So this will be cancelled. So Z becomes equal to under R square. Here Z is equal to R. Just whatever was the resistor's value in your series LCR circuit. If somehow your XL becomes equal to XC, the entire resistance just becomes exactly equal to the value of resistance over here. So what is meant by this? Series LCR circuit is said to be in resonance when current through it has maximum value. Whenever something was present over here, XL minus XC, though this was written, but something was present, right? Something was present. Now that was getting added to the minus XC, then something was getting added to R square, XL minus XC. Yes, class. Now tell me, is it fine? Am I audible now clearly to all of you?
Yes, ma'am.
Okay. Yes, I was saying, see, XL is equal to XC in this case. So when XL becomes equal to XC, the value of impedance becomes exactly the value of resistance. Now, a series LCR circuit, which definition you have to mention in your exam? One definition will definitely be that resonance means when the value of inductance and capacitive reactances become equal, when these values become equal. This will be one definition, but that's not sufficient. A series LCR circuit is said to be in resonance when current through it has the maximum value. This is the definition which you have to mention in your exam. Now, how is this justified? See, when XL minus XC was there in the circuit, this wasn't getting cancelled. We had some value, right? XL minus XC, let it be 1 ohm, 2 ohm, 3 ohm, 5 ohm, 20 ohm, 35 ohm, something value was there that was getting added to R square. So overall ratio was increasing. Now this has been deleted. This entire part, this is 0 in your circuit. So value of resistance has decreased, and maximum value they can be decreased is when they both are equal. So when value of impedance has decreased, value of impedance is minimum. So current will be maximum, because we know current is inversely proportional to resistance or impedance. Impedance is actually resistance. So it is also saying impedance is minimum. Now, when it is saying impedance is minimum, you have to keep in mind you will be using I is equal to VRMS, IRMS will be equal to ERMS or VRMS. Instead of Z we will write it as R. All right, Z because this is equal to R. Or I naught is equal to E naught by Z, and this Z is C. This Z is very less, your current is huge in your circuit. All right, just keep this in mind. Frequency also let us discuss. Frequency is when XL is equal to XC. See, what was the formula of XL? Yes, what is the formula of XL? Faiza. Shahid, right? Yes, Faiza. Formula of XL, inductive reactance. No, Chavez. I'm asking inductive reactance. Faiza. Lambda L. Nu you were saying, I think. Lambda is this symbol, Austin. You must be saying this symbol, no? Nu. Now it's right. Yes, Madiha is also right. Chavez is also right. Yes, Fia is also correct. C class. Omega L. Omega L is the formula, and formula of capacitive reactance is omega C. Now let's cross multiply. Let's just bring this term over that side. So that becomes omega into omega is equal to 1 by LC. So omega square is equal to 1 by LC, right? Now see, omega will be now equal to 1 by under root LC. Also, we know that omega is equal to 2 pi nu. So frequency will be omega divided by 2 pi. That is 1 by 2 pi into 1 by under root LC. This is the value of frequency, and this is the value of angular frequency. This is the condition of resonance. This is valid only for resonance. Just a special case only for resonant. All right. So XL is equal to XC and impedance is minimum. Your current is maximum. Because we know current is inversely proportional to resistance. Resistance is decreasing, current will. Do not write this question. You can write it, or write this question also. You can solve it later. Note it down. Yes, class. See, this says that a resistor of 12 ohm, a capacitor of reactance 14 ohm, and a pure inductor of inductance 0.1 Henry. These are joined in series and placed across a 200 volt 50 hertz AC supply. Calculate current in the circuit and phase angle between the current and voltage. So current in the circuit, for finding out the current, you have to find out the voltage, you need to find out the resistance of the circuit. For phase angle, remember we did tan phi or cos phi, any equation you can use. But see, for the solution of the first part, we need Z this time, because resistor is also connected in our circuit, inductance is also connected in our circuit, and capacitor is also there. So this is a proper example of series LCR circuit, right? So see, value of resistance is given as 12 ohms, value of capacitance is given as 14 ohm, and value of inductive reactance is given as 30 ohms. These are all the values given. Now L, that is inductance, self-inductance, is given as 0.1 Henry. Now we do not know 30 ohms. Okay, 30 ohms is not given. That we'll calculate it. See, 30, how will you get 30 ohms is, L is given as 0.1 Henry. Okay, XL is equal to omega L, and omega is equal to 2 pi nu L. So this is equal to 2 into 3.14 into how much this is given? 50 hertz into 50 into L is 0.1. So when you will solve this, this will become 30 ohm. So that's how I've written over here 30. So now we have all the three values. See, even L, if L was given over here, we didn't know the value of XL. This is L. We want to find out the value of L. Okay. Now see, value of Z. This becomes R square plus XL minus XC whole square, because 30 is greater. So this becomes 12 square plus 30 minus 14 whole square under root. So see, this becomes 12 whole square, 36 minus 14. No, 30 minus 14, that becomes 16. This is 16, this number. Just a second, class. This value, this is given as 30. So this becomes 16 square. This value is given as 16 square. Screen is sharing.
No, ma'am.
Screen has stopped sharing. Just wait. Now see, I have reshared it. Is it still not?
Ma'am, it's sharing.
It's visible, no? Now? Okay, it's sharing.
Yes, ma'am.
Yes, so I was saying this is 30 minus 14. This is 16 square under root. This is 16. So this becomes 144 plus 256. That is root 400, and this is 20 ohms. So value of Z is 20 ohms. Now, this was the question. We had to find out Z. Current in the circuit. Now see, current in the circuit is VRMS. When nothing is mentioned, it means IRMS divided by Z. This is 200 divided by 20. That becomes 10 ampere. This is the answer to the first part. Second part was tan phi. Remember tan phi's formula? I told you XL minus XC or XC minus XL. But this, in this case, we use XL minus XC divided by R. That is 16 by 12. So that becomes 4 by 3. So phi is actually tan inverse 4 pi. This is the value of phase. Note it down. Note down the solution. Question you people have written. Note it down. See what is meant by Q factor. Q factor basically tells you the sharpness of resonance. Resonance occurs at a point, right? When XL becomes equal to XC. So Q factor basically tells the sharpness of resonance. Sharpness of resonance means, is the value of resonance which you have obtained is moderate, or is it severe, or is it high, moderate, or a very low value? Fine. So basically, the sharpness is the exact definition which is helpful and which we remember. That is sharpness of resonance. Sharpness of resonance means what? Sharpness means what? How smooth something is, right? You want to find out when something is going smoothly, what is the maximum value that is achieved? How sharp is the resonant? Is it blunt, right? Is the resonance very low? That is, XL and XC are nearly equal to each other, not very much exact equal to each other. If I say XL is 3.9 and XC is 4, so we'll say, yes, resonance is existing. They are nearly equal. So it's not a very good resonance. When I say both are 4 ohm, so that will be a high value of resonance, right? So it's actually Q stands for quality factor. This Q stands for quality. Quality factor. So quality factor basically tells the quality of resonance. Is it low? Like when we plot the graph between I versus omega, for a very, now see, when the graph is between I versus omega, look here, omega is equal to 1 by under root LC. So a very, very low value of resonance will give you a high value of current. All right, a high value of current. Why? Because resonance is actually determined by the resistances. Yes, XL and XC both are actually the resistances of the circuit. So if it is determined by the resistances of the circuit, so when the current is high, at the highest value of current, see here, at this highest value of current, the type of resonance will be, the type of resistance will be very less, right? The type of resistance will be very less when the current will be more. Now somewhere if I go here, this becomes, this point, this becomes moderate resistance. And when we're talking about this point, this is a very low, a very high value of resistance. Why? Because the values of current, if you see the values of current, that's why. Okay, class. So yes, quality factor. Now, according to the band that we are obtaining, this band, let me tell you this. See, quality factor is what? Quality factor is a series resonant circuit. In a series resonant circuit, this is defined as ratio of resonant frequency. Let me tell you a graph, then only this equation definition will be clear to you. Just pay attention. One graph I will draw, and on the basis of that graph, you'll be able to remember that definition. Otherwise, learning this definition is very boring also, firstly, and secondly, nothing gets into the mind. This is I, this is omega, I versus omega. This is I versus omega. Now see, class. Suppose a standardized portion of the graph I have taken. All right. Now, what are all the points that are available on this graph? This is one extreme point that I'm taking. This is another extreme point I am taking. Now, this is, let's say, the value of angular frequency at resonance, which we are calculating. Omega r is equal to 1 by under root LC. This is it. Okay. Now, these are two different values adjacent to it. I have taken omega 1 and omega 2. This is the value, a very high value that I have taken. I naught is equal to E naught divided by R. Now see this separation between omega 2 and omega 1, this separation. This is called as bandwidth. This is called as bandwidth. Now see, what is quality factor? It's actually the ratio of this omega r. That is the resonant frequency, right? This is omega r divided by their differences, omega 2 minus omega. Now come to the back to the definition. See, quality factor of series LCR circuit, this is defined as ratio of resonant frequency, this is resonant frequency, ratio of, this is what? Resonant frequency to what? To the difference in the two frequencies taken on both sides of resonant frequency. Omega 1 and omega 2, how did we take it? On both sides, on either sides of omega r, yes. So this is saying the same thing. Omega r, this resonant frequency, first in the numerator was resonant frequency. Now, difference between the frequency taken on both the sides of resonant frequency, omega 1 and omega 2. So their difference. All right. That is what we have written, omega 2 minus omega 1. And what exactly omega 2 minus omega 1 is? This is bandwidth. So you can use resonant frequency by bandwidth. Resonant frequency divided by bandwidth. And bandwidth is actually the difference between both the frequencies taken on either side. Now, one more thing that you have to remember, current amplitude becomes 1 by root 2 at the time of resonant frequency. If it is I naught is equal to E naught by R. So at the time of resonance, this becomes E naught root 2 R. This you have to remember. All right. There's a derivation also for the equation of quality factor. Quality factor definition also comes in your exam. Note down all these points, then I'll discuss it. Yes, see what is meant by the high resistance part. When we write the formula of current, current is equal to voltage divided by resistance. So current is inversely proportional to resistance. Here, see, it's zero at the origin, 1, 2, 3, it will be increasing. So the current is highest over here. So if current is the highest, resistance will be the lowest. That's why we are having low value of resistance. So now see I naught. Yes, just see I told you I naught is equal to E naught divided by root 2R. Yes, that's how we write in case of resonance. Now, what is the value of Z? If this is E naught by this, at resonance, we already know that Z is equal to R, right? So it means here, what is the value of Z that we are obtaining when we are calculating quality factor? Z is root 2 times R. We take no Z equal to resistance. Here resistance is root 2 times. So we'll take this. What was the equation of Z? R square plus. Now XL. How can we write XL? XL can be written as omega L minus XC. XC can be written as 1 by omega C. Whole square. This is under root. This is equal to root 2 times R. Now let's square it up, right? To remove this root sign. So this will become square. This becomes R square plus omega L minus 1 by omega C R square. This is equal to 2 R square. So we can shift this over here. So this becomes omega L minus 1 by omega C whole square is equal to R square. Now see, what is the value of R that we can obtain? The value of R is omega L minus 1 by omega C is equal to value of R is plus R. Right? If we take the roots, this is how this is what we are going to obtain. Right? This is clear how we have solved this. R square plus omega L minus 1 by omega C whole square was equal to root 2 R. Yes, right? And this we have squared so that this goes off. Now R square, we have brought this R on this side. So that becomes 2R square minus R square. Yes. So we are left with omega L minus 1 by omega C whole square is equal to R square. And yes, one more thing class, when you will solve this, no, omega L minus 1 by omega C, this is actually equal to plus minus R. Whenever you are taking the roots, it's not just one value that you obtain, it's plus minus. So let's say this is plus, and let's say omega L minus 1 by omega C, this is minus. And two values of frequencies we obtain angular frequency. Remember, let's say this is 1 and this is the second one. Two values of angular frequencies we had obtained in the calculations of quality factor, right? So what we'll do, if we add both these are the two equations which we need. This is equation 1, this is equation 2. Both of these are the equations that we need and solve. Do one thing, class. Firstly, note it down, because I don't think so much time is left that entire derivation will be able to complete. Do it. If time is left, I'll complete it. Otherwise, we'll continue the rest tomorrow. First, note down this from me. This derivation has not been completed. These two equations will now be used further. Okay, class. Now we'll continue derivation from here tomorrow because time is not there. Tomorrow we'll continue from. Okay. Thank you so much, class.